Getting a 100K pay bump in this day and age depends on two things. Number one, the state of the economy, and number two, your ability to answer system design questions. So that's why in this video, I'm going to cover all the technical concepts you need to know as a product manager so that you can ace your next system design interview. Let's get started. This video builds on the system design framework we discussed in the last video. Knowing how to answer system design questions is important, but it's not enough. If you don't understand the core technical concepts behind it, your answer won't be strong. So that's why today we'll be bridging this gap by breaking down the technical concepts that appear at each stage of that framework and how they're relevant to real-world systems. We'll start with the high-level architecture and then move towards concepts you need to know for non-functional requirements and the system design deep dive. And then finally, we'll end off with what trade-offs product managers need to know in their systems. Let's get into it. At a high level, most systems follow a simple pattern. A client sends a request through an entry point, which routes it to the appropriate backend service. This is a classic client-server model. The client is what the user interacts with, like a web app or mobile app. Its job is to capture user input and display information. The server is where the actual processing happens. It checks permissions, talks to databases, and determines what responses to send back. Let's say I'm designing a blog. When a user taps post comment, the app doesn't write directly to the database. It sends a request to the server. The server verifies the user is logged in, validates the comment, associates it with the correct post, saves it to storage, and then returns a response so the UI can update. Now the next obvious question is, how does the client and server agree on what a request looks like? That agreement is the API, and the most common type of API you'll see in systems is called a REST API. REST is a set of conventions for how apps communicate over the internet in a uniform and predictable way. You typically use standard HTTP methods to define what action is happening: get to read, post to create, put or patch to update, and delete to remove. And you use standard status codes to communicate outcomes and responses. 200 means success, 400 means client sent something invalid, 401 or 403 means the user is not logged in or not allowed, and 500 means a server failed. So in a blog system, if a user wants to add a comment to a post, the client might send this to create a comment. If the app wants to display the comments for that post, it sends this to fetch comments. Okay, so in this example, we have a client speaking REST to a comment service that handles all comment-related tasks. But in real systems, there are usually multiple services responsible for different functionalities in the system. Think of it like a company. Instead of one person on the team doing everything, you have your software engineers, your designers, your data scientists, and your PMs. In our blog example, we have a comment service that creates and retrieves comments, a post service that creates, edits, and fetches blog posts, a user service that handles sign up, login, and verifies who the user is. Now that there are multiple services, when a user interacts with the client, how does the app know which service to send the request to? All requests are sent to a single entry point called the API gateway, which sits in front of all your backend services. It routes traffic to the appropriate service, and it also handles common responsibilities like authentication and rate limiting before the request reaches your backend. Think about the API gateway as a reception desk. It confirms who you are, it makes sure you're at the right place, and it directs you to the right team or service. When a user tries to comment on a blog post, the request first goes through the API gateway, which will verify the user's authentication token, apply rate limits to prevent spam, and route the request to the comment service. Services are run on something called a server instance. In a simple scenario, you can imagine a single server instance running the comment service and handling a few requests just fine. But in the real world, thousands or even millions of users might be posting comments at the same time. A single server instance wouldn't be able to handle that level of traffic. So in production, we run multiple identical copies of the comment service. This allows us to handle higher traffic and prevents the system from going down if one instance fails. Now that we have multiple copies running, we need a way to distribute incoming requests across them evenly, and that's where a load balancer comes in. A load balancer is how you spread traffic across multiple copies of the same service. If we have 10 servers that can all handle create comment, we don't want every request accidentally going to server number 1, while the other 9 sit idle. The load balancer will sit in front of servers and distribute requests across the service pool. Think of it like a traffic cop. Its job is to direct traffic efficiently and prevent any single server from becoming overloaded with requests. Great. So far, we've designed how requests move through the system from the client to the API gateway to the load balancer to a service. But once a request is processed, the system still needs to store the results somewhere. If someone posts a comment, that comment needs to be saved. If someone creates a blog post, that post needs to be saved. And that's where databases and storage come into play. Before choosing a database, we first need to define the core entities. In other words, what the system needs to store for the feature or product to work. For a blog, it needs to store users, posts, and comments. Now we want to define how the entities connect and what their relationships are. For the blog example, a user can create many comments, a post can have many comments, and each comment belongs to exactly one user and one post. Because of this, it makes sense to make users, posts, and comments into 3 separate tables in the same database, as they are tightly related and frequently queried together. They may have data fields like this. Now, how does the database actually enforce the relationships between these tables? That's where primary and foreign keys come in. A primary key is a data column whose value must be unique for every row in a table. For example, users have user ID, posts have post ID, and comments has comment ID. A foreign key is how one table connects to another. In the comments table, both user ID and post ID are foreign keys. The user ID references user ID in the user table, and the post ID references post ID in the post table. This ensures that every comment belongs with a valid user and post, which is enforced with the primary and foreign keys. The next decision we have to make is what kind of database do we want for our system? There are 2 main types of databases, SQL and NoSQL. SQL databases are best when your data has clear relationships like users, posts, and comments does, and if you need to query across those relationships. For example, fetch all comments for this post by this user. And lastly, you want strong data consistency by default, meaning you care a lot about your data being correct. NoSQL databases are best when you expect very large scale and you want to distribute data easily across many servers. And also if you can accept some trade-offs in strict data consistency for better scalability. A good example of when to use a NoSQL database is an event logging system. Imagine millions of users generating clicks and page views every second, and the system needs to capture them all. The priority is ingesting a massive volume of data reliably and cost-effectively. In this case, each event is largely independent, and we're not enforcing strict relationships between logs. For a blog, SQL is a good choice for the database because the relationships are simple and well-defined between them. Each comment belongs to a specific user and a specific post, and queries like fetch all comments for this post by this user are easy and reliable to express in SQL. Great. At this point, we designed the core architecture, which includes how requests flow and how data is stored. Now let's move into the deep dive portion of the system design interview, where we improve our system to reflect their non-functional requirements like performance, scalability, reliability and availability, consistency, and security. In this section, I'll explain technical concepts that will optimize the system to meet each of these non-functional requirements. First, let's start with performance, which refers to how quickly and efficiently a system responds to user requests, especially as traffic increases. Systems that prioritize performance include search engines like Google and Amazon Search, where users expect results in milliseconds. Social media feeds like Instagram or TikTok, where content must load instantly as users scroll, or engagement drops immediately and then users go to another app. Productivity tools like Google Calendar, where users expect their schedule to load instantly, otherwise delays can lead to confusion and missed meetings. So what typically slows the system down? In many cases, it's repeated database reads. If millions of users request for the same data, for example, frequently checking the week view in Google Calendar, and every request goes directly to the database, it can quickly become a bottleneck. Databases are not meant to answer the same question millions of times per second. Each query consumes CPU and memory, and eventually the database can't keep up. To reduce that load, we introduce a memory cache. Instead of querying the database every time, we store frequently accessed results in a faster in-memory layer. When the same request comes in again, we return the cache result instead of hitting the database. This works especially well for structured data like calendar events in Google Calendar that are read frequently. However, large files like images and videos require a different storage approach. When users upload media, we don't store those files directly in the database. Large files can slow down queries and increase storage overhead, which hurts overall performance. Instead, we store media in blob storage like Amazon S3 and keep only the file URL and metadata in the database. Blob storage is built to handle large files efficiently and scale independently, keeping the database lightweight and the system fast. But storing the file efficiently is only half the problem when it comes to performance systems. We also need to deliver files quickly to users globally, which is where CDNs come in. A CDN caches copies of those files in multiple geographic locations, so users download media from a nearby edge server instead of your main server. That significantly reduces latency and improves load times. Now, even with caching and CDNs improving performance, there's still a bigger question. What happens as traffic continues to grow? Eventually, the system needs to handle more users, more requests, and more data without slowing down or failing. That's where scalability comes in. Scalability is about designing the system so it can grow smoothly as usage increases. Think of Uber on New Year's Eve. Demand doesn't increase gradually, it surges within minutes as events end and thousands of people request rides at the same time. If the system can't scale, users see long loading times, failed ride requests, or inaccurate pricing, and riders quickly switch to competitors. That's a situation where scalability isn't optional, it's critical for the business. There are two fundamental ways to scale your system. Number one, vertical scaling, and number two, horizontal scaling. Vertical scaling means making a single server more powerful. You upgrade its CPU, add more memory, or increase storage so it can handle more traffic. It's the simplest approach because you're not changing the architecture. You're just giving the server more resources. However, you can only upgrade a single server so much before hitting hardware or cost limitations. And if that one server fails, your system will still go down. With that, let's talk about a more scalable approach, which is horizontal scaling. Horizontal scaling means adding more servers instead of making one more powerful. You run multiple identical copies of your server and distribute traffic across them. This approach scales much further because you can keep adding servers as demand grows. It also improves reliability since if one server fails, others can continue to handle service requests. In most modern distributed systems, horizontal scaling is usually the long-term strategy. However, the catch is that all those servers still talk to the same database. If traffic keeps growing, eventually the database becomes the bottleneck, especially in read-heavy systems where millions of users are fetching the same data. So how do we scale the database layer? One common solution are read replicas. Read replicas are additional copies of your primary database that handle read requests. Writes still go to the primary database, but read traffic can be distributed across replicas. This helps with read traffic, but every replica still stores a full copy of the data, and all writes still go to a single primary database. If the dataset becomes very large or write traffic becomes very high, that primary database can become the bottleneck. Replicas don't fix that because they don't reduce how much data one machine stores or how many writes it handles, but that's where sharding comes in. Instead of copying the entire database like we do with replicas, sharding splits the data into smaller pieces and spreads those pieces across multiple database servers. Each server is responsible for only a portion of the data. That means it also handles only a portion of the traffic. So instead of one database managing everything, the workload is divided across many servers, which allows the system to scale much further. But scaling storage and compute isn't the only way to handle growth. Another important scalability pattern is removing non-critical work from the main request path. For example, in a ride-sharing app, when a user requests a ride, the system should confirm the request immediately. Behind the scenes, it can notify drivers and log analytics. Those background tasks are placed in a message queue and processed by separate workers so the user can receive ride confirmation immediately without waiting for those tasks to finish. These techniques help systems handle overall growth and smooth out bursts of activity. However, in extreme cases, demand can concentrate around a single event, creating hotspots or traffic spikes. Imagine after a Taylor Swift concert ends, Uber can receive thousands of ride requests within a minute. When those hotspots or traffic spikes hit the system, the real question is whether it can continue operating without disruption, which brings us to designing systems to be reliable and available. Reliability means the system consistently produces correct results even when components fail. For example, imagine a banking transfer between two accounts. If the network drops halfway through the transaction, the system must ensure the money is either fully transferred or not transferred at all. It cannot partially debit one account and fail to credit the other. Availability means the system remains operational and able to serve requests, even when some components fail. For the same banking app example, if one server goes down, users should still be able to log in and check their account balance because traffic is routed to other working servers. The system will continue functioning despite the failure. That's availability. Although reliability and availability are different non-functional requirements, they're often discussed together because both focus on how a system behaves under failure. As a result, they can both be improved using similar architectural designs because both require the system to tolerate faults without causing disruption to users. To achieve reliability and availability, we first eliminate single points of failure, which is any component that, if it goes down, brings down the entire system. For example, if you only have one database and it crashes, your entire application becomes unavailable. The most common way to remove single points of failure is replication. Replication means running multiple copies of critical components like servers or databases, so if one instance fails, another one can continue to operate. Earlier, we talked about read replicas in the context of database reads, and replication is the same core idea, which is having multiple copies so the system isn't dependent on a single machine. Alongside replication, the system needs to know how to switch to a healthy copy automatically, which is where failover comes in. Failover is the mechanism that detects a failure and reroutes traffic to a healthy replica. For example, if the primary database crashes, a replica can be promoted to a primary so the application continues functioning with minimal disruption to users. Even with replication and failover, parts of the system may temporarily struggle due to sudden traffic shifts, reduced capacity while recovering, or dependent services not stabilizing at the same time, which can slow down performance even if the system stays up. This is where we introduce graceful degradation. Graceful degradation means the product keeps working in a simpler mode instead of failing completely. For example, in the online banking app, if the credit score service goes down, users can still log in, check their balances, and transfer money. The core banking functions remain available, even though a non-critical feature is temporarily unavailable. To make that possible, we designed the system so the core path stays lightweight and resilient. We use retries for temporary failures, durable queues to push non-critical work like notifications and analytics into the background, and fallbacks like feature flag kill switches or partial responses so one failing dependency doesn't take down the entire page or app. The goal of graceful degradation is simple: keep the main user action available and degrade the nice-to-have features under pressure and stress. So far, we focus on keeping the system fast and available under load and failure, but staying up isn't enough. The system also has to produce the correct outcome every time. Think about an airline booking system. If two users try to book the last remaining seat at the same time, only one booking should succeed. The system must prevent the same seat from being sold twice. So how do we prevent situations like this from happening? One way is incorporating atomic updates. An atomic update means a change either fully completes or doesn't happen at all. There's no in-between state where only part of the operation succeeds. Either all operations commit successfully or the entire transaction is rolled back. For example, when booking the last airline seat, the system must reserve the seat and confirm the payment together. You should never end up with a charged customer and no seat, or a reserved seat without a payment. However, transactions only protect you within a single execution of a request. In distributed systems, requests may be retried due to timeouts or network failures. Even if the transaction is atomic, the same request might be processed more than once. That's where idempotency comes in. Idempotency means that sending the same request multiple times produces the same result as sending it once. It prevents unintended duplicate effects, such as double charges or duplicate records. For example, if a user clicks book seat twice because the page lagged, the system should only create one booking and charge the card once. Even if the request is processed twice, the result must not duplicate the operation. However, not all duplicate or repeated requests are accidental. Some may be deliberate attempts to exploit the system, which brings us to our last non-functional requirement, which is security and abuse prevention. The system must incorporate design principles that can protect the system and its users by ensuring only authorized actions are allowed, preventing malicious traffic from overwhelming the system, and protecting sensitive data. For example, imagine if someone could open Instacart and place 10,000 fake orders in a few seconds. Real customers wouldn't be able to check out, shoppers would be flooded with invalid requests, and revenue for the company would be lost. To prevent this, the system first needs to verify who the user is and what they're allowed to do. And this brings us to authentication and authorization. Authentication answers the question, who are you? As the system needs to verify that the person making a request is a real logged-in user. Authorization answers a different question, what are you allowed to do? Even if you're logged in, you should only be able to request rides for yourself, cancel your own rides, or view your own ride history. Authentication and authorization control who can use the system and what they're allowed to do, but they don't control how aggressively someone can use it. That's where rate limiting comes in. It protects the platform by capping how many requests an account or device can make within a given time window. It prevents excessive activity from degrading the experience for legitimate users. Even authenticated users can overwhelm the platform if they send too many requests in a short period of time. For example, on an online marketplace, a user might message dozens of sellers within minutes about different listings. Each message is valid and authorized, but the volume alone can strain backend systems. Rate limiting controls how frequently requests can be made, but some abuse isn't just about volume, it's about behavior. Basic abuse prevention goes beyond limiting request counts. It's about detecting and stopping patterns of misuse. For example, on an online marketplace, a seller might persuade buyers to take the payments off the platform instead of using the platform's secure payment system. Obviously, this message seems scammy and will degrade the overall product experience as users begin to lose trust in the platform. As a result, we might add safeguards like account verification, device fingerprinting, anomaly detection, or flagging suspicious behavior patterns. The goal is to protect the system and its users from scams, not just spam. So rate limiting and abuse prevention protect the system from being misused, but even if behavior is legitimate, we still need to protect the data itself. Encryption protects sensitive data from being read or altered, whether in transit, between the app and server, or at rest in storage. In an online marketplace, that includes home addresses, payment details, chat messages between buyers and sellers, and account information. Now that we've covered the high-level architecture and the system design deep dive, the final step in a strong system design answer is to step back and explain the trade-offs behind your decisions. There are a few common trade-off patterns that often come up in system design interviews. The first one is the cap theorem, which states that in a distributed system, they can only guarantee two of the following three properties at the same time: consistency, availability, and partition tolerance. Partition tolerance means the system continues operating even when parts of the system can't communicate with each other due to network failures or other issues. In real-world distributed systems, These communication breakdowns are unavoidable, so partition tolerance isn't really optional. That means the real trade-off becomes availability versus consistency. If you prioritize consistency, the system may refuse to process certain requests until it can guarantee the data is correct and up to date. If you prioritize availability, the system will continue responding to requests even if it has to return slightly outdated or temporarily inaccurate data. There are different systems where you prioritize one over the other. For example, a banking app would prioritize consistency. If you transfer $500, the system must ensure the money is deducted from one account and added to another one correctly. If there's any uncertainty, it would rather delay the transaction than risk showing the wrong balance or processing it twice. On the other hand, a social media feed may prioritize availability. It will continue loading posts even if the like count is slightly outdated or a new comment hasn't appeared yet. In this case, staying responsive matters more than perfect real-time data. The next trade-off we have is cost versus performance. Some systems prioritize efficiency and keeping infrastructure costs low, while others are willing to spend more to guarantee faster responses or higher reliability. For example, a startup may limit the number of replicas or caching layers to control expenses, but a mission-critical enterprise system may invest heavily in infrastructure to ensure speed and uptime. And the last trade-off we have is build now versus build later. You can't build for every edge case upfront, so prioritization becomes a key part of system design. What do you want to build now versus build later? Designing for every possible feature and edge case slows development and adds complexity. Instead, focus on core requirements today and architect the system to evolve. For example, when building a blogging platform, you might delay advanced features like multi-author workflows or complex monetization tools until the core publishing and reading experience is solid. And that's it for this video. I hope this was helpful in making system design interviews less intimidating. Just remember, if you're able to translate product requirements for a system into technical decisions and then articulate your trade-offs, you will be a standout in your system design interviews. Thank you so much for watching, it means a lot, and I'll see you in the next one.